Hi everyone. So today we will finish chapter 4. So we'll do 4.5 and 4.6. And I think I'll split this into two videos. So right now we're going to do 4.5 and the next video we will do 4.6. So 4.5, a lot of it is still a review, right? So we did this at the end of chapter 2. And just now we're doing this for a more general vector space where my vectors don't necessarily have to be vectors in Rn. No? But we'll talk about dimension of the vector space again, and maybe just go a little bit more in depth into like proving theorems for this. Right, so recall from what we know before, the vector space with bases containing n vectors is isomorphic to Rn. So we've talked about this a little bit earlier, right? And when we start talking about dimensions, so we know the dimension of Rn is n, right? And dimension was basically defined as how many basis vectors do I have in a basis for my vector space. So our theorem 1 says that if a vector space has a basis of n vectors, then any set in V containing more than n vectors must be linearly dependent. So why is that true? We can look at the proof, kind of get the idea of why this is true. So if I take, for example, if I take any set of p vectors in my vector space V, right, and my p is greater than n, right, so I'm taking a set of vectors where number of vectors is greater than the dimensional number of vectors in the basis of V. If I consider the set of corresponding beta coordinate vectors, right, I just transform each vector into its coordinate vector with respect to the basis beta. So those guys are going to be vectors in Rn because they're just coordinates with respect to beta. We know that this set is going to be linearly independent, right? And recall we did this theorem for when we're testing linear independence of vectors in Rn. If I had more vectors than the dimension n, then the set of those vectors will have to be linearly dependent, right? Because if I put my vectors in the matrix format, or in my augmented matrix with 0 on the right hand side, right, when I'm kind of writing down my linear dependence relationship, if I start doing my row reduction algorithm, because p, number of columns, is greater than n, right, number of rows, whenever I'm doing my row reduction, I might not even have some of the pivots. But there is no way for me to not have free variables. I will definitely have free variables, right? The number of columns greater than number of rows, I will have to have free variables, right? And if I have free variables, then my set will be linearly dependent, right? My columns will be linearly dependent. Right? So, and if that is true, then by definition of linear dependence, if my beta coordinate vectors are linearly dependent, that means that there exist some constants, C1, C2, all the way to Cp, not all zero, such that the linear combination of my coordinate beta vectors equals to 0, right? So I can write down my linear dependence relationship with my C1 through Cp not all 0, right? And so from here we can go further and again write down my linear dependence relationship. I know that such constants exist that are not all 0. Then I also know from the previous class that my coordinate mapping is a linear mapping, which means that my linear relationship holds, right? My mapping of the sum multiplied by constants is constants multiplied by sum. I can split this up. This is basically my definition of linearity of the transformation. So I can basically just put everything into my mapping notation. Right? And then what I'm looking at, I have 0 equals to basically coordinate beta mapping of this one vector. Right? So and here, the best way to look at it, I think your book kind of, when it goes over this proof, it does this a little bit differently. I think the best way to look at it is, remember we talked about this mapping, not only it's linear, it's one-to-one and onto, right? And if the mapping is one-to-one, right, my mapping takes a vector x to its beta coordinate vector. If this mapping is one-to-one, what we know for one-to-one mappings is that if I consider the homogeneous problem, x of beta equals to 0, for one-to-one mapping, the homogeneous problem will only have the trivial solution. Only has the trivial solution. So if beta mapping of any vector x equals to 0, that means that the only solution to this problem is x equals to 0, right? And this is only because my mapping is one-to-one. So when I look at this, right, I have my linear combination of vectors u1 through up, beta coordinate vector, so transformed, equals to 0. Because the beta coordinate mapping is one-to-one, this would imply that the vector inside of my beta coordinate mapping must be equal to 0, because this is my only trivial solution. So it follows from one-to-one property of the beta coordinate mapping. So we basically get that my linear combination of my vectors u1 through up equals to 0, right? But by construction, remember what we started with is that my constants c1 through cp are not all 0, right? Because my beta coordinate vectors, individual beta coordinate vectors of u1 through up are linearly dependent. So on here we basically obtain that this linear combination I can construct such that not all c's are equal to 0. So my vectors u1 through up are also linearly dependent. And so again, it basically follows from the fact that any set with more elements than the basis vectors in the basis is linearly dependent. It basically follows from those properties of beta coordinate mapping that it is one-to-one and it is linear, right? And the fact that in Rn, any set that contains more vectors than n dimension is going to be linearly dependent. And then this theorem also we can rephrase a little bit, right? We can rephrase it if a vector space V has a basis with n vectors, then each linearly independent set in V has no more than n vectors, right? So I mean, it's basically just restatement of this theorem 1 in different words, right? So I cannot have a linearly independent set with more than n vectors because I have n vectors in the basis. All right, so it's very useful, powerful theorem. Then we have the next theorem. Again, this kind of dealing with the bases and the number of vectors in the bases and things like that. So the next theorem says that if a vector space V has a basis of n vectors, then every basis of V must contain exactly n vectors. And there's kind of a second part. The first part said that I can't have linearly independent set with more than n vectors. But here we're going from the opposite direction, saying that, I can't have a basis having kind of less than n vectors, or obviously more than n vectors. So and this one is easier to prove, right? So suppose we have a basis beta of n vectors, so that one is given. And suppose we have another basis of p vectors, so say, for now I don't know what p is, but suppose I do have another basis of p vectors. Right? If it is a basis, my beta 2 is going to be linearly independent. And by the previous theorem, right, if I have an independent set of vectors in a vector space of dimension n, then the number of those vectors has to be less than or equal to n, because if it is greater than n, then my set would have been linearly dependent. Right? But we can also go kind of in a, switch them around, right? I know that beta 2 is a basis, right? It's given to me. And beta 1 is linearly independent because it's a basis, right? So I can also say because beta 1 is linearly independent and beta 2 is a basis, then n has to be less than or equal to p, right? Because if a vector space has a basis with p number of vectors and beta 1 is a linearly independent set in that vector space, then I cannot have more vectors in this linearly independent set than the number of vectors in the basis. So we can basically get that p is less than or equal to n, and then it's less than or equal to p, so n must be equal to p, right? So if I have any basis of a vector space, then all of those bases have to have the same number of vectors. All right. And then to our definition. So again, we already talked about, dimension of the vector space and things like that, but we only talked about this in the context of Rn. And now we're doing it in the context of a more general vector space. All right, so we'll define a more general definition of dimension. If a vector space is spanned by a finite set, then V is said to be finite dimensional. So when we're dealing with Rn, those were our finite dimensional vector spaces. And the dimension of V is denoted by dim V. It's basically the number of basis vectors for V. So for Rn, our dimension was n because we have n vectors in the basis for Rn. And then we also had a little exception, right? So we can have a zero vector space, a vector space containing only the zero vector, and the dimension of the zero vector space is defined to be equal to 0. Right? And then, since we're dealing with more general vector spaces now, we actually do have some vector spaces that are infinite dimensional. So some vector spaces may have infinitely many basis vectors in them. Right, so we have some examples of all of those, right? So we've dealt with Rn, right? We can take the standard basis for Rn, consisting of columns of the identity matrix of dimension n by n, right? I have n basis vectors, so the dimension of Rn is n, right? So we did those examples before. But now for more general vector spaces, we talked about a vector space of all polynomials of degree at most n, right? And the standard basis for this vector space, right? I'm just taking all of the different powers of my variable t1, t squared, all the way to tn, right? So if you count the number of bases, right, I have 1 through n, and I also have a constant, right, 1. So my dimension of Pn is going to be the number of the basis vectors, which would be n plus 1, because I'm kind of plus 1 to the power 0 of t. But the infinite dimensional vector spaces, one example you can think about is, you can have a space of all polynomials, not just polynomials of degree at most n, but all polynomials of all possible degrees. Right, in this case, when you're writing down, say, the standard basis for this vector space, you will have all of the different powers of t. So 1t, t squared, t cubed, and kind of this list continues, and continues on and on, right? We're not terminating it on some greatest power n that the monomials may have. All right, so this would be our first example of an infinite dimensional vector space, because I have infinitely many basis vectors. Right, we can have some more examples here. So how do you find dimensions of a vector space? So if I'm just given a set, right, that happens to be also a vector space or a subspace, right, how do I find the dimension? So for this example, basically I want to be able to figure out, well, how many different linearly independent basis vectors do I have here? right? So I'm given set H defined as, basically it's going to be subset of R4, right? So my 4 coordinates is defined in terms of A, B, and C, where A, B, and C are some real numbers. All right, so I'm basically taking some linear combinations of vectors here. If I write this out as a linear combination, all right, if X is an H, then I'm just factoring out like A, B, and C, and D, right, and writing everything out in terms of the vectors. So each X in H can be expressed as a linear combination of those 4 vectors, right? But be careful because, yes, this kind of the span of those four vectors will be equal to my subspace H of R4. But do those vectors necessarily form a basis? I don't know yet, because remember, for the basis, my requirement is that not only they have to span my subspace, they have to be linearly independent. All right, and here we have a subspace of R4. If I have all 4 linearly independent vectors, then 4 linearly independent vectors will generate a subspace of dimension 4. So if all of those are linearly independent, that means that H would be equal to R4. All right, so we really need to check whether H is all of R4, or maybe some of those vectors are linearly dependent and I can throw some of them away to form the basis. So to find dimension, I really need to find the basis of linearly independent vectors. Right? So, all right, if I consider the span of those 4, and the main question I need to answer is whether they're linearly independent. Right? And there's a few ways to do it. You can put everything into your matrix form, right? And do your row reduction and see if look at your pivots and see if your columns are linearly independent. Or you can kind of make your life a little bit easier and just kind of start going through some of them and see if maybe some of them are linear combinations of one another or multiples of one another. So if I just start with V1, one vector by itself is linearly independent, right, if it's not equal to 0. So, okay, V1 is fine. Then when I go to V2, well, 2 vectors are linearly independent if they're not multiples of one another. So is V2 a multiple of V1? Definitely not, right? I have 1 in the third position, I have 5 in the second position, and 0 in the second position in the second vector. So they're not multiples of one another. So V1 and V2 are linearly independent. Then when I go further to V3, I can notice that V3 is actually a multiple of V2, right? I have -3, 6, 1, and -2, right? So V2 and V3 is a multiple -1/2 times V2. So V3 is linearly dependent. It is a multiple of V2. So remember our theorem we did last time is that if I kind of get to one vector that's a linear combination of the previous ones in my set, I can discard it and my span does not change because of it. So if I just completely remove my V3, the span is going to be exactly the same. All right, so I'll discard V3. My span will be exactly the same. And now I also have vector V4. So now I have 3 vectors and I need to figure out if they're linearly dependent or independent, right? So I have V1, V2, and V4. If I look at V4, I can't immediately tell if it's a multiple of V2 or V1, right? So in this case, you do need to do a little bit more work, maybe put it in your matrix form, right? So my V1, V2, and V4. Do your row reduction algorithm until you get to the point where your pivot columns and rows are obvious, right? So over here, if I was solving it as an augmented system at 0, 0, 0, 0, it's obvious that my rows are going to have to be linearly independent, right? Because setting this equals to 0, the only solution is going to be 0, 0, 0 for all of the constants. Right? So that's fine. I mean, that just tells me that my vectors are linearly independent because the columns here are linearly independent. And if I have a linearly independent set of vectors that span the subspace, it has to be the basis. Right? So my basis is going to consist of vectors v1, v2, and v4. And because I have three vectors in my basis, the dimension of my vector space or subspace of a vector space V, which is R4 in this case, is going to be 3. Right? So again, just kind of don't rush things when you do those problems. Always check your conditions, right? If I want to find the dimension, I want to find basically the number of the basis vectors. And over here, it looks like, well, maybe those are basis vectors, but I'm not given anything here about linear dependence or independence of those guys. All I know is that v1, v2, v3, and v4 span H, but I don't know if they're linearly independent, so you have to check that. And in this case, they actually were linearly dependent, so you have to get rid of the ones that introduce this linear dependence. So, okay, and since we're talking about subspaces, remember when we were talking about subspaces of R3 or R4, I mean in general Rn, right? So subspaces of R3, I mean we have basically options defined by dimension, right? I can have R3 is dimension 3. So all of the subspaces of R3 would basically go from 0 to dimension 3. The zero-dimensional subspace is just a zero subspace. The one-dimensional subspace is a subspace spanned by one non-zero vector, which, as we saw before, would be lines through the origin. Right? If I have one vector v1, the span is going to be all of the points on the line that has to go through the origin. Otherwise, it's not a subspace because it will not contain the zero vector. Then two-dimensional subspaces would be spans of two vectors, right? So if we're in R3, those are vectors in R3, right? We know that the spans of two vectors in R3 are going to be planes through the origin, right? So provided those vectors are linearly independent. If those vectors are linearly dependent, it's basically the span of just one vector and again the line through the origin. Right? And the very third case is basically the subspace is a vector space itself, right? When my H is R3 itself, this would be the span of three linearly independent vectors in R3. And you can expand this to kind of all subspaces of Rn, right? You would just be going, if I had R4, then I would be going all the way to kind of four-dimensional subspaces of R4, or n-dimensional subspaces if I'm looking at Rn. Right, so for Rn, it's not pretty straightforward. Right, so we have one more theorem here. So if H is a subspace of a finite dimensional vector space V, any linearly independent set can be expanded if necessary to a basis of H. Also, H is finite dimensional and dimension of H is less than or equal to dimension V. So I mean, so the last statement is pretty obvious, right? I mean, a subspace of a finite dimensional vector space should also be finite dimensional with smaller dimension, and kind of like we saw in this example. But the first condition, I mean, we can prove this right now. I mean, this basically gives us sort of a recipe for building bases for subspaces of the vector spaces, right? So if I have a linearly independent set, maybe it's not a basis for my subspace yet, but I can basically expand it, kind of add more vectors to it to generate a basis, right? In other words, it says that any linearly independent set is a subset of some basis for that subspace. Right? So we can go through the proof here. I mean, kind of simple case, if H is just a zero subspace, then dimension of the zero subspace is 0. obviously it's less than dimension V, right? But otherwise, say if I have some set S of k vectors that is linearly independent set in my subspace H, right? So I have k linearly independent vectors. So if span of S already equals to H, then we're done, right? S is a basis for H, because for basis I need linearly independence and I need the span to be equal to H. So then we don't really have to do anymore. But the other option is if I have linearly independent vectors u1 through uk, but the span is not equal to H, right? Then that means that there is some other vector uk plus 1 that belongs to H, but it does not belong to the span of my set S, right? I mean, that follows from the fact that span of S is not equal to H, right? So kind of like span of S is a subset of H, but not all of H. So I can basically take, this is my span S, and my H is just larger. So I can take some U k plus 1 that's not in span S, but is in H. Right? And I'll just add it to my set. Now, is this set linearly independent? It actually will be automatically linearly independent because, why? The original set was linearly independent, right? U1, U2 through UK. By adding another vector, my set would be linearly dependent if this vector is a linear combination of the preceding vectors, right? But because uk plus 1 is not in the span of S, I know that uk plus 1 is not a linear combination of all of those vectors u1 through uk. And since uk plus 1 is not linear combination of those vectors, then my resulting set here will be linearly independent. That makes sense? So, and you can basically continue this expansion to larger and larger linearly independent sets S in H, right? So basically, add another vector, sets linearly independent. Does the span of S equal to H? If it does, then S is a basis. If it doesn't, add another vector, right? Again, it will be linearly independent because the next vector will not be in a span of the previous ones. All right, so you can continue this procedure over and over and over until span of S equals to H. Right? And then by theorem 1, any set in V of dimension n containing more than n vectors must be linearly dependent, right? So the number of vectors in linearly independent set cannot exceed dimension V. So when I'm continuing doing this procedure, I mean, eventually span of S will be equal to H. And this dimension of H has to be less than or equal to dimension V because otherwise my set of those vectors U will be linearly dependent. All right, and that basically concludes the proof of this theorem here. All right, so we'll do another one. So also concerning basis. So this theorem says that it kind of basically makes it a little bit easier for us to search for bases. Right? So this theorem is called the basis theorem, and it says that if V is a p-dimensional vector space with p greater or equal to 1, then any linearly independent set of exactly p elements in V is automatically a basis for V. Also, any set of exactly p elements that spans V is automatically a basis for V. So, I mean, basically what it says is that when I have p-dimensional vector space V, and I'm looking for my basis, I really just need to find p vectors that either are linearly independent or span V. If I have p linearly independent vectors, then automatically they will span my space and be a basis. Or if my p vectors span my vector space V, then you can show that they'll automatically also be linearly independent and therefore form a basis. Right, so we can prove this also, right, and it's basically a consequence of all the previous theorems we did today. right? So by previous theorem, any linearly independent set of p elements can be extended to a basis, right? So kind of looking at this part of the theorem. But the basis has p elements, right? We know because dimension v is p. So this set is already a basis. I don't have to expand it any further, right? So p linearly independent vectors in the vector space of dimension p will automatically be a basis, right? Because I should be able to expand it generally, but here I don't have to expand it anymore because I already have dimension p. And we showed in the previous theorem that this is enough. Right? And then the second part, so suppose the set of p elements spans my vector space V, right, of dimension p. Then remember our spanning set theorem. There is a subset S prime of S that is the basis for V, right? So I think we did this theorem last class, right? So if I have a spanning set for my vector space V, then some subset of the spanning set will be a basis. Alright, so I kind of did this in the previous example too. Remember when we did the H, right? We had a spanning set V1, V2, V3, and V4, but only a subset of this was the basis, right? We got rid of V3, and the subset V1, V2, and V4 was the basis. Right, so that's kind of what we're talking about here. Right, but here again we're looking at condition that since dimension of V is P, right, then my basis must contain P elements, right? That's definition of dimension. And because my set S has P elements, my spanning set S has P elements, its subset that generates a basis must have P elements. So S must be equal to S prime. So again, just if you find a spanning set of P elements for the vector space of dimension P, then it has to be a basis. Right, so again, we just basically have to kind of using the dimension of a vector space, we can basically focus on just finding a spanning set of P elements or a linearly independent set of P elements, and this will automatically be a basis. Okay, so maybe let's do a couple more examples. So again, it's kind of a review, right? So we kind of kept coming back to column spaces, row spaces, null spaces. All right, so and here we'll just review a little bit what we did in chapter 2, right? And also in this chapter, like the only thing we haven't really reviewed from chapter 2 is this rank nullity theorem. Right, but remember, column space is basically the space spanned by columns of the matrix A, right? And if I want to find the basis for this, what we were doing is we were taking spans of just the pivot columns of A. And then dimension of the column space, another name for it is rank of A. So rank of A is dimension of the column space, right? For row spaces, row space of A is the span of the pivot rows of A, which forms the basis. So again, kind of review here. Dimension of the row space will be equal to dimension of the column space, because if I'm counting pivot rows and pivot columns, the number of pivot rows and pivot columns is the same, right? It's just the number of pivots that I have. So dimension of row space will be always equal to dimension of the column space. And I kind of have a maybe shorter way for writing this. It's the rank of the matrix A. For null spaces, it was a little bit more implicit when we're looking for kind of like basis vectors and dimension for null space. The null space is basically the solution set of the homogeneous problem, AX equals to 0. And when we take in the spans of basis vectors for null spaces, what we had to do is we had to basically find the general solution for the homogeneous problem, write it down in the vector format, and then pull out those vectors to form a basis for the null space, right? And the number of those basis vectors for basically corresponding to the number of free variables I have in my system, right? Because each free variable gave me kind of an arbitrary constant, right? And then when I factored everything out, those free variables were weights on the basis vectors for the null space, right? So the dimension of the null space, right, would be the number of the basis vectors for the solution set of the homogeneous problem corresponding to a number of free variables, and another name for it is nullity of the matrix A. So nullity is dimension of the null space. And then kind of from all of this construction follows the rank nullity theorem, right? Because when we're looking at our kind of columns of the matrix A has n columns, right? Number of pivot columns gives us rank, or dimension of the column space. And the columns that are non-pivot columns are the columns that give us free variables, right? And the number of free variables or number of non-pivot columns give us the number of those linearly independent vectors in the general solution of the homogeneous problem. So that gave us the nullity. So from this follows this kind of nice relationship that rank of matrix A plus nullity of matrix A equals to n, which is the number of columns of A, or dimension of the domain, right? So again, we did this in chapter 2, but all of this applies to more general vector spaces, right? Also, well, kind of in more general context. All right, so let me do, I have one more kind of review sheet here. So in regards to column spaces and null spaces, if I have a matrix A, right, I want to find my column space, null space. What I generally do, I bring it to some row echelon form, right? So if I did my row elimination algorithm, my row echelon form of A is matrix B. I identify my pivot columns. I identify my non-pivot columns. If I just want to know the rank and nullity, number of pivot columns will be my rank. So here I have pivot columns B1 and B3. And then the rest, my non-pivot columns, B2, B4, and B5, gives me my free variables. So when I write down my solution, I would have each individual constant corresponding to each one. So dimension of the null space or nullity of A will be equal to 3. And overall, I have 5 columns, right? So by my rank nullity theorem, rank 2 plus nullity 3 equals to total number of columns equals to 5. And the very last thing, again, we did this before, so we're not going to do very much of it, but just to review the invertible matrix theorem, right? My matrix A is invertible is basically equivalent to all of those different conditions, right? If A is invertible, columns of A form a basis for Rn, right? And I'm looking at A n by n matrices. Now, if columns of A form a basis for Rn, it means that all of my columns are linearly independent, right? So column space of A equals to Rn, right? Columns of A form the basis for Rn. Rank of A equals to n, right? Because, rank is the dimension of the column space. Column space is Rn, rank is n. With nullity, those two groups are basically connected through rank and nullity theorem, right? If rank is n, then nullity has to be equal to 0 because rank plus nullity should be equal to n, right? And nullity equals to 0, null space must be equal to 0 space, right? Because 0 vector space is the only vector space that has dimension 0, right? So those groups are connected through rank nullity theorem. And you can go from here to here also. So we did all of this before, right? So, but just kind of to review, like if you wanted to show that matrix A is invertible, you can basically just look at the rank or just look at the nullity, things like that. So all those things are connected. So we basically finished 4.5. here. And a lot of it was kind of a review from what we did in chapter 2. I mean, we did a little bit of new things. So in the next video, we're going to do chapter 4.6, and this one is going to be, we haven't done this before. Right, we'll do this in the next video. So in 4.6 would be the last section in chapter 4. And we will basically talk about how to change bases if I have a vector x expressed in terms of coordinate in one basis. What if I want to convert this into a different basis? I mean, maybe it's easier to compute things in a different basis. It could be a different number of reasons, but we want to be able to quickly convert from kind of one basis or one coordinate system to another coordinate system. But we'll do this in the next video.